Herzlich willkommen zur Vector Virtual.
A warm welcome to the Vector Virtual Week 2020. I'm Michael Epping, and today I would like to give you an introduction into charging communication for electric vehicles. In my presentation, I would like to show you which charging technologies are on the market. Then I will show you which standards are relevant. And then I would like to show you a live demonstration for an ISO 15118 procedure. These are the charging technologies which are available on the market already. On the top left, you see the wired charging, which you know already. Here we have AC charging and DC charging. Apart from charging, the cable is also used to communicate between the vehicle and the charging station. On the right-hand side, you see wireless charging. This is inductive charging, where the energy is transferred via coils. And since we don't have the cable anymore, the communication is also wireless. In the commercial vehicle area, we also have pantograph charging. Here we have two variants. On the bottom left, you see the inverted pantograph, where a mechanical system is integrated in the infrastructure and moves down to touch upon the vehicle roof, and there are two bus bars on the roof. Since this vehicle is controlling the charging communication, we also use Wi-Fi in this case, and this triggers lowering the pantograph. Right next to it, you see the roof-mounted pantograph. Here the mechanical system is installed on the vehicle roof, and it moves from the bottom to the top once the vehicle is in the right position. The standard describes Wi-Fi to be used in the future, but today these projects are still using the technology from connector charging, so this is power line. In the future, there will be more charging technologies. For example, it is conceivable that a robotic arm plugs in the connector. This is very comfortable for the driver, but it's also a fact that the charging cables become heavier and heavier. A DC cable is already quite heavy today, and in the future they will be water-cooled and the weight increases. So it is not so easily possible for everybody to plug in a cable like this. Next to it, you see the underbody connection device. This can be compared to the pantograph. Only this technology is installed underneath the vehicle, and an arm moves from the parking up to contact the vehicle. For wired charging, we see that several connectors have been established. This depends on whether you want to charge AC or DC, and there are also regional differences. In North America, the Type 1 connector is used for AC charging. And for DC charging, this connector has been expanded by two more pins, which is the combined charging system, CCS. A similar system is also available here in Europe, but here the connector is called Type 2 connector or CCS Type 2 connector, because the geometry of the connector is slightly different to Type 1, and therefore it's not compatible. Both systems are using power line for the communication. And that is different to the Asian standards CANoe and GBT, which use CAN for communication. The two Asian standards are currently merging into the Jiao-G standard. At present, they are working on a joint connector geometry, and we expect that in the future the communication protocol will also be standardized. Tesla still have their own connector, but these vehicles are also now available with a CCS inlet. So let's have a look at the CCS system in detail. In the center, you see the inlet on the vehicle, And on the left-hand side, you see the Type 2 connector, which is used for AC charging. It only fills up the upper part of the inlet, and the lower two pins, which are used for DC charging, are only used by the CCS connector, which you see on the right. The pins that are colored in orange on this picture are used for AC charging, and that's why the CCS connector doesn't have them. The upper pins, which are colored in blue, are used for the communication, and therefore they are available on both connectors. The proximity pin makes it possible that the connector is identified, and the control pilot is used to communicate between the vehicle and the charging station. Let's have a look into the vehicle. This is a schematic drawing of the charging system of a vehicle. On the left, for AC charging, you have the Type 2 inlet or the CCS inlet. But here an additional component is necessary. That's the onboard charger. And this converts AC into DC, which is then used to charge the battery. Additionally, there is a communication component. And via the control pilot, it communicates with the charging station. And this component is also in charge of controlling the charging procedure, and that's why there can network between the onboard charger and the battery management system. In the case of DC charging, this onboard charger is not necessary. Here we just have a second pair of contactors for safety reasons. And the charging voltage for the battery is generated by the charging station. In the table at the bottom, you see a quick overview of the pros and cons. The charging power is much higher at DC charging. With wired charging, we are now at 150 kilowatt, and it will be more in the future. And for AC charging, it's now at 11 and 22 kilowatt, respectively. The onboard charger has additional weight, and it requires extra space, which is not necessary for DC charging. However, the charging station is smaller for AC charging, and it's less complicated, whilst at DC charging it includes a lot of technology, and also with these high charging powers, these devices are very complex and therefore expensive. Let's have a look at the standards which are necessary for communication. I start at the bottom. The IEC 61851 specifies the communication through several parts. So it specifies the physical design of the connections and the basic signaling. This technology is enough to realize a charging process for AC. This means that passenger cars that are supporting AC are usually based on these standards. And if you want to charge DC, or if you want to use additional features for charging communication, a CCS system requires a high-level communication. And for this, we have the standards DIN 70121 or the ISO 15118. And apart from this, there are institutions and associations who publish additional documents, for example, to close specification gaps. One large representative is CANoe, and they published guidelines for plug and charge, but there are also German bodies like the VDE. They published a document that describes the handling of certificates in the backend. As I said, the ISO 15118 has several parts. There is the -1 document, which contains general information and use case definitions. And for a little while, a second edition has been published. And then there are several documents that describe the different network layers. -2, for example, describes the network layer to the application layer. The -3 document describes the communication via power line. And for the future charging technologies, we have the -8 document, which describes communication via Wi-Fi. And then, matching it, there are test specifications for the respective documents. And these test specs allow the manufacturers and suppliers to test the integration of the protocols. And for this, we have conformance tests in place, which automatically tests whether the protocols have been implemented according to the standard. And this is then the basis for the interaction with other systems. For the -2 document, we currently have an elaborate revising, and it will be published next year within the -20 document. And this document includes new charging technologies and new key features, for example, the recuperation, so that the vehicle can also feed energy to the infrastructure. And it also standardizes how the communication is to take place for inductive charging, the wireless power transfer, WPT. And there's a new mode, automatic connecting device, ACD. And I showed you some examples for this earlier on. For example, the pantograph, but also the robotic arm would go into this category. And of course, there were lessons learned from the -2 document. And therefore, many small improvements were introduced, which are partially listed down here. For example, it was agreed upon having the communication always encrypted by TLS. And now let's have a look at the protocol stack to see which protocols are used. I already said that for the communication between the vehicle and the charging station, the DIN 70121 and the ISO 15118 are specifying user protocol, which is optionally encrypted via TLS. And all this is based on an IPv6 DEC and is then transferred via power line to the charging station. The charging station typically has a second interface to the backend. Here, OCPP is used for communication. This is a protocol based on WebSocket, and it's also encrypted via TLS, and in this case, it's transferred via IPv4. And then there's the special case, the value-added services. Here, the vehicle can communicate directly with the backend, for example, a charging station management system. One example for this would be, for example, that you build up an HTTP connection, which goes from the vehicle to the charging station and is then routed into the backend, where the connection is then processed. And now I would like to give you an example for an ISO 15118 communication. On the right-hand side, you see the state machine for this protocol. It's quite elaborate. And until you really get the power, you have to go all the way to this state. You see, a lot is happening before the battery is actually being charged. And now I change into our tool, CANoe. This is a tool for the analysis and simulation of network communication. And here you can see a simulation from a vehicle on the left-hand side and a charging station on the right-hand side. For the communication, I select the ISO 15118. I say I want to charge with DC, without plug-in charge. And now I virtually connect the connector. And then you see that the communication starts immediately, and we'll wait a few seconds until the battery has been charged in the simulation. So now you see energy transfer has started. You see that the bar is rising, and now the battery is fully charged, and the vehicle ends the communication. And now we can have a look at the beginning of the communication. Here in black, you can see the so-called slack protocol. This is necessary because at power line there is a very high crosstalk, and therefore it's not always clear for the vehicle with which charging station it is communicating. And the slack protocol now makes sure that there is a point-to-point connection. This is then followed by the SECC discovery and the supported app protocol. This is a handshake which communicates about whether encryption is going to be used via TLS and which protocol versions are going to be used. For example, it could be that the vehicle supports DIN 70121 and ISO 15118, while the vehicle or the charging station only uses one of them, and here they agree upon which one. And then there is a number of messages to prepare the charging procedure, for example, the authorization and the exchange of charging parameters. And in the case of DC, there is also an isolation check and a pre-charging, and then it starts charging in the charging loop. Here, the vehicle sends in cycles the current demand request. And at DC charging, it specifies with which current and which voltage the battery is to be charged. The charging station confirms the request. It first of all says, OK, it has been accepted. And then it also confirms the parameters which are currently in use. Both messages also include limits to make sure that the voltage or the current will not become too high. Once the battery is fully charged, the vehicle ends the charging loop. And then in the welding detection, it makes sure that the contactors have opened completely. And in the last step, the communication is finished. So this was now fast forward through the communication. Thank you very much. And now I'm looking forward to your questions.
Und freue mich jetzt auf Ihre Fragen.